So this is your last problem on effort and power of governor. That's a Hartnell governor problem. So in a Hartnell governor, the length of the ball and the sleeve arms of the bell crank lever are 120 mm and 100 mm respectively. So ball arm is X and sleeve arm is Y respectively. The distance of the fulcrum of the bell crank lever from the governor axis is 140 mm. So this is your R. So what is the fulcrum of the bell crank lever? We know very well. So at the equilibrium mid speed for a Hartnell governor, I mean the average speed n1 plus n2 by 2, the ball arm is vertical and the sleeve arm is horizontal. Okay, and the governor axis is somewhere here. Okay, so this distance is R. So at lower speeds less than this average speed, your arm will be inclined like this. Sleeve will go down due to the lesser speed. Okay, so now the ball will be here, right? So at higher speeds, the ball will come out due to centrifugal force, and the sleeve will move up due to this. Here is your governor axis. So if you notice very carefully, in all the three cases, this L-shaped bell crank lever is hinged at this fulcrum point. So this R does not change with the position of your governor; it remains constant. Okay. So this is R, no change, right? So what is R1? At the lower speed N1, ball center to the governor axis distance is R1. Okay. At the average speed, the radius of rotation is equal to R because your arm is vertical. At a higher speed, this is your radius of rotation R2. So if from observing these diagrams, I can draw one conclusion. So for a Hartnell governor, R1 is always less than R, R2 is always greater than R. So please have a look carefully. So this R is a fixed constant value for a given governor. R1, R2 can keep varying based on the speed. Clear? So this is a Hartnell governor fundamental. Just keep that in mind very clearly. So you will have that diagram for you to have a look for some few more minutes while I complete the question. Each governor ball has a, so that fulcrum point radius is 140. So this is your fulcrum point radius is 140. Okay. Each governor ball has a mass of 4 kg. This is your small m. The governor runs at a mean speed of 300 rpm. So speed related to this position. Okay, this is 300 rpm with the ball arm vertical and sleeve arm horizontal. So that's what I have drawn here, L shape, vertical and horizontal. Okay. For an increase of speed of 4%, the sleeve moves 10 mm upwards. Okay. So 4% increase in speed, sleeve moves upwards means what? It is from the equilibrium position to higher speed position. So therefore this is H2. H2 is 10 mm. Okay, right? With that in mind, now I'm going to read the questions listed down. Neglecting friction, find minimum equilibrium speed if the total sleeve movement is limited to 20 millimeter. This is total H. Okay, what is H? Come back to this diagram. Now, from this position, okay, let us say that all these three have a single line. So now, as the sleeve movement, as the speed goes very high, the sleeve moves upwards. This is your H2 from equilibrium to upward, higher speed. From equilibrium to downward sleeve movement is H1. Okay, so total H1 plus H2 equal to H. Clear? So do you understand what is H1? This is H1. I mean, this is H2 higher speed. This is H1 lower speed. So this is given for a 4% change in sleeve, 4% change in speed. The sleeve moves upwards by 10 mm. So that is H2. Upwards means from equilibrium. Upwards means it is a higher speed. N2 case. So that is your H2 10 mm. Total is 20. This total. So from here to here is 20. Therefore, if this is 10 and the total is 20, so the remaining will be 10. Clear? That's it. So that is the first question. Find minimum equilibrium speed. That is N1. Okay. Second question, spring stiffness. Third question, sensitiveness of the governor. Fourth question, spring stiffness if the governor is to be Isochronous at 300 rpm. This is a new one. So isochronous, I already told you in the introduction video. Uh, Isochronous means it is like a cutoff switch. So until the 300 rpm, the sleeve will be at the lowest position. Once you reach 301 rpm, it will be at the highest position. There is no intermediate, extremes only. Okay, so that is a isochronous governor. So for this Hartnell governor to function as isochronous, to behave as isochronous governor, what is the spring stiffness required? So that one you are going to find out. So these are the 4 questions. Now let us list down the given data. So the ball arm length is 120 millimeter, which is 0.12 meter is X ball arm. Sleeve arm is 100 millimeter, which is 0.1 meter. So radius of rotation at the fulcrum point radius is 140 millimeter, it's 0.14. So ball mass is 4 kg. Equilibrium mean speed is 300 rpm. So convert that into 2 pi n by 6, it comes around 31.42. So H1 is 10, H2 total H is 20. Actually, this should be H2. Okay, H2 is 10. Total height is 20. Clear? Let's move into the problem. Minimum equilibrium speed N1. Let N1 equal to minimum equilibrium speed. R1 equal to radius of rotation at that minimum equilibrium speed. So this R1 is from the ball center to the governor axis. Okay, only R is measured from the fulcrum point. R1 and R2 is measured from the ball center to the governor axis. R2 is the radius of rotation for maximum position, higher speed N2. Okay, since the increase in speed percentage is 4% for maximum speed, so N2 is equal to N plus 4% of N, where N is your equilibrium speed, where your governor will be like this vertical horizontal position. For that is N is 300. So 300 plus 4% of 300. So that is 1.04 N. 1.04 of 300 is 312 rpm is the maximum speed. Okay, the maximum speed the governor can operate is 312 rpm. So convert that into omega, it comes around 32.7 radians per second. Okay, so I'm just doing 2 pi n by 60. So 312 rpm is nothing but 32.7 radians per second. Okay. We know that the lift of the sleeve for maximum position H2 is H minus H1, it's 0.02 minus 0.01. So it's, see, one of the thing is 10 millimeter. So total is 20, the remaining is 10 millimeter, 0.01. Now for minimum position, just note down this relationship. H1 by Y equal to R minus R1 by X. H1 by Y equal to R minus R1 by X. So this is a similar triangle relationship. If you go into the obliquity relationship, you will understand that you have to go back and refer the fundamentals of Hartnell governor. So this formula you remember, H1 by Y equal to R minus R1 by X. So you rearrange this formula for finding out R1. Okay, so send everything to the left side. So R1 equal to R minus H1 into X by Y. Okay, so R is 140, 0.14 meter, H1 is 0.01 meter, X is 0.12 meter, Y is 0.1 meter. Okay, put all the numbers into this equation. So in place of this R, I am going to write 140, 0.14, H1 is 0.01, X is 0.12, Y is 0.1. So solve this, you will get the radius of rotation first, minimum speed. So it comes around 128 millimeter or 0.128 meter. Similarly, for maximum position, H2 by Y equal to R2 minus R by X. As I already told you, R2 is greater than R because the ball will be outside. So center of rotation, from the ball center to the axis of rotation, fulcrum point. So this is R, this is R2. Okay, so therefore R2 minus R. But here is R minus R1 because the ball will be inside. In the minimum speed case, fulcrum point will be outside. Okay, it will be something like this, not like this. Okay, so fulcrum point radius will be somewhere here. So R1 is less than R, but R2 is greater than R, therefore R2 minus R. Okay, so rearrange it for R2 formula, R plus H2 into X by Y. So R is equal to 0.14, H2 is 0.01, X is 0.12, Y is 0.1. Substitute all the numbers into the above expression. So R is 0.14, H2 is 0.01, X is 0.12, Y is 0.1. Solving this, you will get R2 as 0.152 meter. Right? So now I know both the radius. So I can now find out the centrifugal force. So now I know the one of the speeds. Maximum speed I know 312 rpm. So mean speed is 300 rpm. Minimum speed I am yet to find out. Okay. So let's have the mean speed omega here 300 rpm. So centrifugal force at the mean speed position, okay, this is the mean speed position. The value of Fc is equal to m omega square r. So this is 4 kg, this omega is 300 rpm omega, so that is 31.42. R is this fulcrum point radius 140 millimeter, okay, that is 0.14. So if you multiply all these things, you will get 553 Newton as a centrifugal force at the equilibrium position. Okay, next, centrifugal force in the minimum position. Here one problem, we don't know the value of omega or n for the minimum position. Okay, so Fc1 equal to m omega 1 square r1, right? So m is 4 kg, omega 1 is unknown, so keep it as it is. R1 is just we have found out 0.128. So in place of omega, I am putting 2 pi n1 by 60 the whole square. Instead of omega square, I am writing 2 pi. So this should be in the power. Okay. So 2 pi n1 by 60 the whole square. Because omega equal to 2 pi n by 60, right? In place of omega 1, I am putting n1. So solve this, you will get a relationship between Fc1 and n1, 0.0056 n1 square. Okay. So keep it as it is. Therefore, Fc1 equal to 0.0056 n1 square. So second case, higher speed case, Fc2 is equal to m omega 2 square r2. So it is this case where the ball is traveled outside, sleeve has gone up. Okay, so this is your r2, which is greater than your fulcrum point radius, r2. Okay, so this r2 also you have found out as 152 millimeter, 0.152. Okay, ball mass is 4. This is 312 rpm. The position for r2 is 312 rpm, which is 32.7 radians per second. Solve this, you will get 650 Newton. Clear? So keep everything as it is. So now I know average point centrifugal force, maximum point centrifugal force, minimum speed centrifugal force only is unsolved still. Keep it as it is, right? So centrifugal force at any instant. So this is a new formula for you. Please note this down. This interrelates all these centrifugal forces. Fc is equal to Fc1 plus difference between the maximum and minimum centrifugal force multiplied by r minus r1 by r2 minus r1. Okay. So this is a new formula. Please make a note of this. It's a relationship between all the centrifugal forces. So Fc is 553, Fc2 is 650, R is 140 or 0.14, R1 is 0.128, R2 is 0.152. Put all these numbers into the above equation. So only Fc1 is unknown. So this is Fc is 553 Newton. I am putting 553 here. Equal to Fc1 is unknown. Keep it as it is. Fc2 is 650. Again Fc1 is unknown. Keep it as it is. So R is 140, 0.14, 0.14. R1 is 0.128, so put 0.128 here, divided by R2 is 0.152 minus R1 is again 0.128. So I am going to simplify this and find out the value of Fc1. Okay, so do cross multiplication, adjustments, all that, and then you will finally find out that centrifugal force for the lower speed case Fc1 is 456 Newton. Okay, now this is equal to 0.0056 n1 square. So I can equate that and find out the value of n1 square. 0.0056 n1 square is equal to 456. Cross multiply, you will get 456 n1 square is equal to 81,428. Take a square root of that, you will get minimum equilibrium speed position is 285.4 rpm. So this is n1. You have answered the first question. So hence the minimum equilibrium speed n1 equal to 285.4. First question you have answered. Let's go for the second one. Spring stiffness. Right? Let S1 and S2 be the spring force at minimum and maximum speed. Okay. So at N1 speed, the governor position will be somewhat like this. It is less than average speed. Okay. So sleeve is here. There is another symmetric arm like this. So we are not going to consider that. So the spindle has a spring which is pushing the sleeve down with the force of S1. Similarly, at the speed S2, spring is exerting some force, and against the force the sleeve has travelled upwards. Now this case you have a force of S2 at a RPM of N2. Okay, so this is S1 and S2 spring force. Here keep that in mind. So S1 and S2 equal to spring force at minimum and maximum position or minimum and maximum speed. Okay. Neglecting the effect of obliquity of the arms, we have what is the neglecting the effect of obliquity. So we do not consider x1, y1, x2, y2. We directly take x and y, because this variation creates a difference in height. See, it's like this. Arm is equilibrium position, minimum speed position, maximum speed position. Now this height is not equal to this height, correct? All are different, but the difference is very small, so I am totally ignoring that. That is ignoring the obliquity. Okay, so it is approximate, reasonably approximate. Okay, so neglecting the obliquity of the arms, you have minimum position. This relationship, this you know from the Hartnell governor derivation. So sleeve mass and gravity plus spring load divided by 2 into y. So this comes by taking moment. Okay, so this is in the center. Mass of the sleeve plus spring force, half of that is acting on one side, half. So we are doing only a mirror half symmetric half analysis. Therefore, only half of the mass comes to one side of the sleeve into y equal to FC1 into x. Okay, this moment is taken about the fulcrum point. Okay, so for that, for minimum position, mg capital Mg plus S1 by 2. So this distance from the fulcrum point, it is located at the distance of y. It's actually y1, but I am neglecting the obliquity, it is y, equal to centrifugal forces here from the fulcrum point Fc into this is x. So that's how this formula comes, by taking moment about the fulcrum point. Okay. Capital Mg plus S1 by 2 into y equal to Fc into 1 into x. So I am neglecting the gravity effect. It is given in question, neglecting gravity. Okay, therefore I am neglecting this. Therefore the formula gets simplified. So S1 by 2 into y equal to Fc into x, Fc1 into x, cross multiply and rearrange the formula for finding S1. So 2 Fc1 into x by y. So Fc1 is 456, x is 0.12, y is 0.1. Put all the numbers into the above equation. So Fc1 is 456 Newton, x is 0.12, y is 0.1. Solve this, you will get the spring load at the minimum equilibrium speed N1. So it is 1094.4 Newton. So spring load at the minimum equilibrium speed on the spindle is on the sleeve is 1094.4 Newton. Similarly, I am going to find out the value of S2. mg plus S2 by 2 into y equal to Fc2 into x. Okay, this is also same thing. Take moment about the fulcrum point O. Okay, so take m is equal to, neglecting the gravity effect, this equation gets simplified. Rearrange for S2. So Fc2 is 650 Newton, x is 0.12, y is 0.1. Put all the numbers into the above equation, you can find out the value of S2. Okay, so this is 650. 0.12 is x, 0.1 is y. Solve this, you will get S2. 1560 Newton. Okay, so now I know both the values of S1 and S2. So spring stiffness is equal to S2 minus S1 by h. This is a standard formula. So S2 is spring load on the sleeve at the maximum speed. So this is the minimum speed. This is the total sleeve lift. Okay, so when I substitute the value of h in millimeters, I will get the spring stiffness in Newton per millimeter. If you do it in meter, you will get the stiffness in Newton per meter. You can do the whatever the way you want. Normally, you do with millimeters for stiffness alone. In all other places, only meters should be used in calculation. Okay, so S2 is 1560, S1 is 1094.4. Total sleeve lift. Don't use H1 or H2. Entire sleeve lift you have to put here. 0.02, 20 millimeter. Okay, so put 20 here in the fraction. So therefore 1560 minus 1094. So this is S2 is 1560, S1 is 1094. Don't think S1 minus S2. Greater value minus smaller value, difference. Okay, divided by 20. So that is going to give me spring stiffness of 23.28 Newton per millimeter. Hence, spring stiffness S is equal to 23.28 Newton per millimeter. Second question is answered. Right. Third question, sensitiveness of the governor. Formula for sensitiveness of the governor. We have seen this in the introduction. So 2 into N2 minus N1 by N1 plus N2. Okay. So you know that N1 is 285.4, N2 is 312. Put all these, both the values into the above expression. So N2 is 312 minus N1 is 285.4 divided by N1 plus N2. Okay. So solve it, you will get 8.9 percentage. The answer should be given in percentage. Okay. So sensitiveness of the governor is 8.9 percentage. So third question is answered. Finally, the fourth question, spring stiffness of the governor for to behave as isochronous at 300 rpm. Okay. So here for isochronous behavior, we have to keep one thing in mind. N is equal to N1 is equal to N2 is equal to everything is equal to 300 rpm. Here, whatever may be the radius of your balls, wherever it is, anywhere, the speed should be 300. It is practically not possible. You may think that it is what it is meaningless, all that, but all the speeds are equal. Okay, so beyond that, your deflection will be maximum. Below that, it will be minimum. That is the isochronous behavior. Okay, so convert this into omega. So it comes around 31.42 radians per second. Now what I'm going to do, I want to find out the spring stiffness for this case. What is the formula for spring stiffness? S1, S2 minus S1 divided by H is the spring stiffness formula. So what I'm going to do is I'm going to keep the speed as constant. I'm going to use R1 and R2 and find two centrifugal forces, M, this omega square R1, M, the same omega square R2. I can find out two centrifugal forces, Fc1 and Fc2. Using that, I can use the relationship of stiffness and centrifugal force. I can take moment about the fulcrum point O and find out S1 and S2, then I can find the stiffness. That is the methodology. Okay. So now find out the centrifugal force with radius 1 for the same 300 rpm, omega 31.42. Okay. So ball mass is 4 kg. This 300 isochronous speed. So 31.42 square. R1 is 0.128, so it comes on 0.05. Similarly, Fc2. In Fc2 also you have to use the same speed because it is isochronous. Otherwise, you have already found out the Fc2. But here only for 300 rpm you are doing everything, right? But it is not equal to Fc, average centrifugal force, because the radius is different. Okay, for all radius you are going to have the same speed. That is the isochronous behavior. Okay, so 4 into 31.42, that is 300 rpm omega square into R2 maximum radius 0.152 gives 600 Newton. Okay, now I am going to take moment about the fulcrum point. S1 equal to 2 Fc1 into xy. So using that Fc1, now this new Fc1 value you substitute into this relationship, 505.5 new F1 Fc1 centrifugal force into x by y ball arm sleeve arm. So S1 is 1213 Newton. Similarly S2, new Fc2 600 Newton is substitute here. 600 Newton into 0.12 by 0.1 multiplied by 2. So this gives 1440 Newton. So S2 is 1440 Newton. Now I know that the sleeve lift is the same. Okay, 20 millimeter maximum travel of the sleeve. So that is same. So therefore I can now easily find out the stiffness of the spring. S2 minus S1 by H. So 1440 minus 1000. So S2 is 1440 minus 1213 divided by the entire sleeve lift 20 millimeter. So this gives me a spring stiffness of 11.35. So therefore, hence spring stiffness required for isochronous behavior of the Hartnell governor at 300 rpm is 11.35 Newton per millimeter. It means what? If you put a spring inside the spindle which is having a stiffness of 11.35 Newton per millimeter, this governor will behave isochronous about 300 rpm. So until 300 rpm you will have no deflection, and at 301 rpm you will have full deflection. So that is isochronous behavior. Do you understand? So that completes the problem. Let us summarize the results. So minimum equilibrium speed N1 285.4 rpm, spring stiffness 23.28 Newton per mm, sensitiveness of the governor is 8.9%, and finally the spring stiffness required for isochronous behavior at 300 rpm is 11.35 Newton per millimeter. So that completes the problem. This is taken from your Kurmi textbook, problem number 18.27. Thank you.